Hi everyone, welcome to Data Structures and Algorithm, session 6, and this has content of the heap and the priority queues. As you know that we have done the tree, and following that we are looking at the examples of tree, and heap happens to be one of those which is implemented using the what you call complete uh, binary tree, and hopefully we'll have a discussion on Q&A at the end. But before that, let me hand over to Jaimit Osava, who is going to go through this data structure algorithm session 6 on the heap and priority queue. Thank you very much. Go ahead. Take over, Jaimit, from here.
Sure. Thank you so much for the introduction. So hello everyone. This is Data Structures and Algorithm session 6, which will be focused on heaps and priority queues. So let's get started with the heaps. So heaps, what are they? So they are trees organized so that we can determine the node with the largest or the smallest value quickly. And not necessarily all the trees are heaps, but heaps are represented in terms of or implemented in terms of trees, not completely following each and everything what we have followed in trees, but similarly, what are priority queues? So in a priority queue, data is organized in a heap so that we can determine the node with the next highest priority quickly. So priority is different depending on the case, use case, and that it is being implemented on. So you can say that priority queues are implementation of heaps. So why are they important? What are their uses? So heaps and priority queues, why should we use them? So let's say we have the task of getting the largest or the smallest element from the set where there are many insertion and deletion operations are taking place. So one way to get this largest or the smallest element is to sort the data and get the element and get the largest or the smallest whatever is needed out of them. So but the reason but a drawback to this method of following or getting the largest or the smallest value is it is expensive to do it over and over again when there are many insertion and deletion operations are also happening, and it takes a lot of time in a way. So we need a more efficient manner. So another method is that we can store these values that we need frequently and grab them from the wherever we have stored them. So let's say now applications of heaps and priority queues. So first is sorting. Before so sorting is basically organizing the stuff. So first is a heap sort. So it is a comparison based on sorting algorithm where a max heap is built from an array and repeatedly extracts the maximum element to create a sorted array. Then next is a quick sort, which is also a comparison based sorting algorithm where smaller and smaller subarrays are formed recursively to sort and in the end to sort these subarrays. But in practice, the quick sort happens to be just a bit more more efficient in its implementation by a small constant factor. Then next is a task scheduling, which is performed by operating systems to determine which process is next to run on CPU. Operating systems continually change the priorities of processes. So a priority queue is an efficient way to ensure that the highest priority process is next to get the CPU or the a resource. Anyway, next is parcel sorting. So uh, whenever delivery companies or delivery services and they need to prioritize the parcels for urgent or high priority parcels need for getting faster or quickly delivered. So for that we can use them, and we can use a priority queue for in the computer system for ensuring the parcel priorities. Next is Huffman coding, which is used for data compressions, where codes are assigned to symbols in the data. If the symbols occur very frequently, shorter codes are assigned to them, and longer codes for less frequently occurring symbols. So the Huffman tree is built by merging small binary trees two by two, and then the two trees merged at each step are extracted from the priority queue because we merge the two with the smallest key values. Then it's it's a load balancing. So often usage statistics are maintained about a number of servers handling similar tasks or handling different kinds of requests. So a priority queue can be used to determine which server is best able to accommodate a new request, or even if the servers are uh, as mentioned here are handling similar kind of tasks. So how a server can be can be chosen to accommodate a new request. So starting with the heaps, and a heap is a tree which is usually a binary tree. So trees, as discussed, they are there are nodes along every branch. They have nodes, and they do have a specific order to them. Then they are, but the trees here that we will be using, they are partially ordered, which means that left side of left subtree or right subtree are not balanced with respect to each other. They can be balanced in a subtree wise, but not in respect to each other. So if we sort the if we sort the heap where parents are larger in value than the children's, or parents have more value than the children's, then it's called a max heap or a top heavy approach. And if we approach the heap in a way where children have a higher value or a larger value than their parents for the organization, then it is called a mean heap or a bottom heavy approach. So heaps are left balanced trees, which means that if we insert values or nodes into them, then they will grow from left to right until that level is filled, and then go to the next level. So for storing nodes contiguously, we will represent these left balanced binary trees as an array. So we'll be implementing heaps in terms of array. And and the zeroth, for the zeroth indexed arrays, and for some position I, uh, the parents of a node is I minus 1 divided by 2, and we'll be ignoring the fractional part. So we'll be taking the closest integer, which is smaller or equal to the integer that we have gotten. And for the position of the left child of it is given by 2i plus 1, and for right it's 2i plus 2. This very thing will be implemented whenever where we'll be uh, discussing the code further. So this organization is important to locate the last node. So this is the implementation of this is a graphical representation of a heap. So you can see how starting with uh, index 0, which is 25, it goes from left to right. So 0, 1, 2, 3, and you can see the corresponding nodes also, and how in image A it shows us the tree, in image B it shows us the implementation of it in with the help of an array. So starting from index 0, 20, which has the value 25, to index 10, which has a value 18. So interface for heaps, or basically the normal head the normal operations that we'll need for implementation of heaps. So first is heap init, which basically initializes the heap, and you can see within heap there is a compare function which compares key 1 and key 2. So if we are approaching it in a top heavy heap manner, then then we'll get the value of key 1 is greater than key 2 will return the value of 1. It is not assigning the value of 1, but rather returning it the value of 1. So key 1 is greater than key 2 will return the value of 1. Key 1 equals to key 2 will return the value of 0, and key 1 smaller than key 2 will return the value minus 1. See, this reverses when a bottom heavy heap is used. So key 1 is greater than key 2 will give us minus 1, will return us minus 1. Key 1 equal to key 2 will be same, and key 1 smaller than key 2 will return us 1. For heap destroy is uh, uh, it's a operation for deallocating the memory for the heap. Then heap insert for inserting a node that is specified by the heap pointer. Then extract for extracting the node which is at the top of the heap, and heap size for telling us the size of the heap. So this is just a header files for the heaps implementation. So so you can see first we have struct heap, and the size, compare, destroy, entry are used in its structure, and member element heap. Then we have the heap init, destroy, insert, extract, and heap size that we just discussed. So let's first see an insertion in the how an insertion in the list or a heap, sorry, how an insertion in the heap is done. So let's say, sorry, just a second. Sorry, how sorting of in heap is done. It's not, please ignore the example for insertion. So you can see that we start with the actually it is sorry. So the insertion is actually happening, and so whenever we do an insertion in the node, so new node will be uh, introduced into the array at the very last position. So this is what you can see after 10th element, which is 18th. We have added 24, so it comes into the 11th position in the array. And now after insertion, we will be resorting or reheapify the array. So so as 10 is smaller than 24, we'll swap its position. So when we will be swapping, we'll be also please have a look at the array and its position also. So as you can see that we have swapped the value of 24 with 10. 10 goes into the 11th position and 24 at the 5th. Now, as 22 is smaller than 24, we'll again swap it. And now, as it is sorted in a way, so we won't be needing any more swaps. So for what we have seen for the insertion or how insertion works in an array, heap insert will point to the data of the new node given, then allocate the space for the new node, and this node is entered into the last index position of the array. So and then we reheapify, which is basically to rearrange the tree for the heap property. Heap property basically is that parents have a larger value than the parents are larger than the child. That's it. So how do we reheapify? So starting at a new node, we move up the tree level by level, comparing each child with its parents. So that's what we did here. That we compared 24 with 22, and if rearrangement or they are in wrong order, we'll swap their position. So we swapped their position and repeated this until we reached at the top of it, or no swaps are required. In our example, we didn't require any swap. And then in the end, we update the size of the member of the tree structure because we added or we inserted a new node. Then there is a heap extract. A heap extract operation extracts the node at the top of the heap. So the data will be used to point to the node being extracted. We save the contents of the last node, give smaller storage to tree, and decrease the size with 1. So here you can see the extraction of 25. So you can see that on the root node we have 25 and we are extracting it. And whenever we extract it, we'll swap the position of the root node which is being extracted with the last node that is in the tree, or sorry, in the heap. So you can see that now 18 will be appearing in the at the root node, and we'll be swapping it with 22. And after swapping it with 22, we don't need any other swapping. So our tree is sorted, our heap is sorted. So this is the same header file for the heap that we saw in the slide. The structure of the heap, then the initialization, the destroy heap, insert, extract, and the size of the heap. Now the implementation of the heap in the C program. So remember that for the heap parents position, we had the formula of n-1 divided by 2, and for the left and the right, we have 2n plus 1 here, 2n plus 1, and for the right, we have 2n plus 2. So So first is the initialization. For the as we initialize, we'll be initializing with these values, and then we have the heap destroy function for deallocating the memory. After deallocating, we use the free for freeing the storage, and uh, memory set for a precautionary measure. Then next we have heap insert. So heap insert here will be using the temp, the I pause for current position and P pause for the parent's position. As you remember, for the whenever we inserted, we compared the child with its parents, and if the swap was needed, we swapped it. So first we will be allocating the storage, but for what any reason, if it's not successful, it will return -1. If if it's not, then if it's successful, then it will uh, initialize the operations in the allocated space. We first remember that any new node inserted will be inserted in the last node. Then we will be uh, swapping the position with the parents when as far as we needed it, and if it's done on that level, we'll move up the level also, and when it's done, finally we'll increase the size of the heap. Next is heap extract. Heap for this we'll be using the save function, the temp function. Save for the extracted node, I pause for current, L pause for left position, R pause for right position, and M pause for maximum position. So for the node containing the maximum value, for it being the root node in the end. So this is just a check for the empty heap. Then we start with the node. As I said that first we will be saving the extracted node. Then adjusting the size, and also managing the last node as while extracting. Then copying, as you remember, the extraction happens in a swap between the last node and the root node. So this is what it's done, and it's save is used here. Then in the end, the swapping happens for the reheapification of the heap, and this is the condition to check where the heap property has been stored. Then swapping the contents of the current node and the selected child, and move down the level. And in the end, for the whole, and in the end, for the whole of the function to successfully being carried out, it will return 0. So Next after heaps is implementation of heaps with the help of priority queues, or as implementation of heaps as priority queues. So Wiki's definition to priority queue is a priority queue is an abstract data type similar to a regular queue or stack data structure, and each element in a priority queue has an associated priority. So heaps are great to implement priority queues, and using priority queues for load balancing. So maintaining the usage statistics about a number of servers to balance load. This is something that we have discussed at the starting of the presentation about load balancing and using the servers. Uh, how to determine which server is the best suited to serve the new connection request. And the server with the least usage is the highest priority. So for the implementation of the priority queues, similar to the heap init, we will be using priority queue init for initialization of the priority queue, and and similar to the heap, here we will also be using the compare function, and the larger key are if the larger keys are a higher priority, then key 1 greater than key 2 will return us 1, key 1 equal to key 2 will 0, and key 1 smaller than key 2 will return us -1. For a priority queue, as a smaller key is a higher priority, then key 1 greater than key 2 will give return us a -1. Key 1 equals to key 2 will return 0, and key 1 smaller than key 2 will return us 1. Then a priority queue destroy is basically the function to deallocate the memory. Then queue insert is inserts an element into the priority queue specified by PQ. Then PQ extract for the extracting the top element from the priority queue specified by the PQ. Then peak for peaking the for using a PQ peak for peaking the value, and uh, PQ size for giving us the size of the specified priority queue. So how do you implement it? Uh, First, we have to maintain a sorted data whenever we implement a priority queue. As insertion and extraction operations need to resort the set, the worst case complexity of it becomes a big O of n. So one way to keep the set partially ordered using a heap, so is using a heap. So resorting the heap after the insertion and extraction takes only big of log n complexity, because we are only partially ordering, keeping the heap ordered. So using the priority queue for parcel sorting. So as you remember the delivery service application that we discussed at the beginning of it, delivery parcels delivery parcels are used, and if you give more charges, then they have the service to deliver the parcel faster. So the delivery services or companies handle millions of these parcels, but they have a limited space. So if let's say if they have to deliver the parcel next day, and a way to get the parcel on and there is a plane that is going at certain destination where they have to deliver the parcel next day, then they will keep that they will, without any mistake, they have to keep the parcel there on the plane to get it delivered and onto some uh, onto its designated destination. So how do they apply it or implement it? So going to a certain destination, parcels are processed. Sorry. processed according to correct priority, and their information is stored in the priority queue. So as sorting begins, the parcels with the higher priority are added first. So why use a priority queue? So a priority queue is a good way to manage parcels because at any moment we are interested only in the parcel with the next highest priority. So therefore we can avoid the overhead of keeping the parcels completely sorted. So for the implementation of the uh, parcel sorting, we'll be using two functions which are put parcel and get parcel. So put parcel is a structure is from a structure of parcel to load the information about a parcel into the system, and one member of the parcel structure passed out to the parcel put parcel function is a priority code. The next is the put parcel function inserts a parcel into the priority queue, which prioritizes the parcel among the others. Then when the sorter is ready to move the next parcel to get to the next parcel, it calls the get parcel, which gets the next highest priority parcel and are processed in the correct order. So let's look at the implementation of the parcel. First, will be there will be three header files that we'll be using. So starting with the heap.h that we discussed, we have the typed of heap queue, then init, pq init, pq destroy, pq insert for insertion, extraction for the top extraction, then peak, and then size. Next is the parcel for the defining a structure parcel first, and then having a priority in it. Then the get parcel and the put parcel that we just discussed. So first we start the implementation using by including the needed header files. Then we use the get parcel. First it checks whether there are any parcels or not, and if for some reason it is not able to retrieve the parcel, it will give us the -1 code for unsuccessful carrying out of the operation. And but if it is successful, uh, it will return back the parcel that was needed. Then it's a put parcel for the implementation of parcel sorting. So first we allocate the storage for it, and check for it too whether it's successful or not. If it's successful, we insert the parcel into the priority queue, and if for some reason if it's not, then it will use the corresponding for it. And if the whole success if everything is successfully carried out, then it will give us the exit code of 0 for successful execution. So this is it for the codes and the theory that was related to the heaps and priority queues. So let's get to the some of the questions and answers that we have. So first is to build a heap from a set of data using the interface presented in this chapter, in this presentation. We call heap in the set. So since heap insert runs in log n time, as it is done only partially. So building a heap of n nodes require n log n time. So what is the alternative to the approach that runs in big O of n time? So so uh, answering this question in a brief manner, we can take a bottom to top approach, and we while keep on sorting it, we can uh, we can get to the root level and get the whole tree sorted and have the complexity of big of n. As as you can see that it is the same thing and thing being mentioned, and on the last third line, when calling heap insert repeatedly, half the heapifications could require traversing all log n levels in the worst case. Thus, building a heap in this way runs in a big of n log n time. So question 2. So what are a heap parent, heap left, right defined in heaps? Why are a heap parent left and right defined in .c? And whereas macros of size was defined in heap h. So there are certain controls that we don't want to give or don't want to be carried out. So that is the reason why it was given in that manner. And as in the answer, you can see that a developer using a heap should not be permitted to traverse a heap's node indiscriminately. Instead, access of the heap is restricted to those operations defined by the interface published in heap.h. Now, moving to question 3. Recall that left balanced binary trees are particularly well suited to arrays. Why is this not true of all binary trees? So to state it briefly, if we use a right balanced binary tree in if and you can imagine the array, then all the you can sometimes have uh, a left node and then all sorry an element and then all the elements between them, and the rightmost element at the end of the array or somewhere between the array can a uh, have a blank space between them, which is one of the reason that a left balance tree is used. So 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 suppose a binary tree of 10 levels is completely full through 9 levels, but in the 10th level, only one node resides at the far right. Remember the structure of the tree and the array, how they are transferred. So that is the reason. So on the 10th level, only one node resides at the far right. So in the contiguous memory storage, the node at the far right of the 10th level resides at the position 2 raised to 10 minus 2, which is 1022. Using a zeroth index array, the node at the far right of the 9th level resides at the position 2 raised to 9 minus 2, which is 510. So this results in 5 511 empty positions out of the total 1023 positions required to represent the tree. Thus, only 50% of the array is being used, and that is one of the reasons why left balance trees are used. Next question is, suppose we are using a priority queue to prioritize the order in which tasks are scheduled in by an application. So if the system continually processes a large number of high priority tasks, what problems might the system exhibit? How can we correct this? So, whenever an an OS has a stack of high priority tasks being conducted continuously, whereas the low priority tasks are sitting there and are not getting the chance to be serviced. The one way to implement is that as time progresses, the low priority tasks their priority increases with time, and eventually getting at the top in order to get serviced, and they are not starved of the CPU time. So last are the Fibonacci heaps, which is a collection of so this is just a topic uh, for the heaps. So Fibonacci heaps is a collection of heap ordered trees. Fibonacci heaps are used sometimes in computing minimum spanning trees and finding single source shortest paths. Then there are k-array heaps. K-array heaps are instead of binary, we have a certain number of nodes or child nodes or a branching factor. So heaps with a branching factor of k, although not as they are not much common in the binary trees. They do have a certain way to solve some problems or issues. So yeah, this is it for the heaps and priority queues. And thanks a lot for listening.
Hey, Jamit, very good. Aditya had dropped in and he left, and
Okay.
the question and answers you have covered. So hopefully this will be a good place to stop, and
Yeah.
we will uh, address the next uh, the related to tree something which binary search tree, and I'll share with you all the information, and we'll see how we can get it on Friday. Okay.
Yeah.